Hello, my name is Gareth Barnaby. I'm here presenting Autogrip, a project from my PhD that I've worked on alongside my supervisor, Dr. Anne Rodell. I'm going to introduce our project with our video. So, why did we build Autogrip? I've been working with force feedback technology for a number of years, and as part of my work I do a lot of public engagement and demonstrations, specifically with fingertip feedback. Force feedback robots can use thimbles, a small cup, to connect a device to a fingertip. Typical designs are pretty effective from a haptic perspective, although they suffer some problems in specific scenarios. One problem is that the human form is quite inconsistent. Finger sizes vary a lot amongst people. So any thimble based on springs or elastics will apply more pressure to a larger finger and less pressure to a smaller finger. And this is a problem, as pressure from the thimble will stimulate or can even saturate tactile receptors in the skin. Some thimbles get around this by either having different sized attachments for different sized fingers, or by instead using manually adjustable mechanisms, such as Velcro straps. But these manually adjustable mechanisms suffer their own problems in that they're quite cumbersome and impractical, especially when you're dealing with multiple point systems, and even more so if they're bimanual systems. In multiple user applications, it's still very impractical to swap between different sized attachments. In my case, if I'm showing a 2-minute demo, taking a minute to swap attachments between users is a lot of time and work. It also affects many people's first impressions of a force feedback system. People don't want to wait for a minute while the demonstrator measures their finger and refits the machine. So, we wanted a thimble that could be easily and rapidly attached to any finger, and that's why we designed Autogrip. Autogrip consists of two parts, the thimble itself and the separate actuator module. Separating the two means that the thimble itself can be very light, this is good for reducing mechanical inertia, and also very small, which is good for multiple point systems. If you like pinching, the thimbles won't interfere with each other. We've made quite a few design revisions on our actuator, and the most recent design is just two 3D printed parts and one N20 gear motor. So fishing line is tied to the spool, so pulled on by the motor as it turns. The base section can be attached anywhere on a haptic device. The thimble itself is made in two parts, held together by the fishing line. The line is routed through springs in each corner, so pulling on the line closes the thimble, releasing the line lets the springs push it open. A single wire capacitive antenna is embedded in the upper section, so Autogrip can not only self-adjust, but autonomously grip onto a finger placed inside it. This is very useful for automatically detecting if a finger falls out, particularly helpful for admittance-controlled haptic devices. We implemented two modes of attaching the thimble, combining it with a leap motion to track the position of a user's hand. In semi-auto, the user places their finger into the thimble, which automatically adjusts itself. The leap motion means they can also do this in VR with a headset obstructing their vision. In full auto, the user just holds out their hand and the control algorithm guides the haptic device onto their finger. We compared these modes with the manual Velcro strap method through a small study with 7 novice participants, measuring how quickly they could each attach the thimble. We found that the semi-auto methods were particularly effective at attaching and adjusting quickly and reliably, although we found quite a wide range of results for the full auto method. We attributed this to participants inadvertently hampering the algorithms by attempting to assist themselves, and also some inconsistency in the accuracy of the leap motions tracking. Besides our study, we have done a large amount of in-field testing with the prototype, mostly using the semi-automatic mode. In the field testing, it has performed its function very well, working reliably across hundreds of users, even going in between children and adults with no fuss. So this brings us on to our first topic of future work, which is improving the full auto algorithm. While we found it could be effective for trained users, future work must go into making it much more robust towards novices. We also think it would be interesting to investigate active tactile sensations. There is quite some literature investigating using thimble design to augment the haptic experience. So we think consistent grip strength that Autogrip offers could be beneficial for particularly microfluidic or electrotactile systems. We also think it will be interesting to try applying it to different form factor devices. So far, we have only applied it to grounded 3D force feedback devices, although it would be interesting to investigate applying it to devices such as force feedback gloves. And finally, we think it would be very interesting to apply it to different body parts. A fingertip is an easy place to start, however, the concept could become even more effective as more body parts are included within a haptic feedback system. Maybe we've missed some ideas in our future directions, so we have published the design files along with our paper so that anyone can 3D print and experiment with their own. Autogrip has been developed alongside and integrated with another of my projects, Mantis, creating affordable force feedback technology. I ran a number of demos of my haptic devices, ranging from a simple swing ball script and the highly popular teapot curling game, to more complex applications such as real-time virtual wind tunnels, where the haptic interface allows users to adjust the simulation in real time. Recently, I've been developing some experimental VR cursors to provide powerful 3D interactivity with a fingertip. A multi-tool cursor lets users intuitively place, delete, move, lock and unlock, and interact with virtual objects. I'm very excited to be commercialising my work with a startup, Zenmag Robotics, that is focused on producing affordable, high-fidelity haptic feedback technology. Please visit my website to find out more or to get in touch.